Let's talk about SNR, why those calculators don't work, what does work, and why it doesn't matter at all. Welcome to SETI Astro. Now, it does seem like that there has been some talk around SNR lately. I've seen a couple videos with people making their own SNR calculators. I know Deep Sky Detail has one. Dylan O'Donnell just came out with one. Pix Insight itself has a script for SNR. I want to talk about those, why they don't work, a script I had written a while ago that you may not have even noticed was in my repository, and why in the end none of it really matters. To start with, I have a single frame from my red channel for IC342, and then I have a master light composed of about 50 stacked exposures. And this is kind of what we're going to use to talk about SNR, and in the end, ultimately, why I don't think it really matters a whole lot. So Pix Insight itself has a script. Under Script, Image Analysis, SNR. If you run it, it will just give you a quick SNR reading for the whole image. In this case, it says it has a signal to noise ratio of 39 decibels, which doesn't mean a whole lot, or about 8,000, right? 8 times 10 to the third. So they're saying that this particular image, this red channel, has about 8,000 times more signal than noise. If we go ahead and look at the single frame, we could run the same SNR analysis again. In this case, it dropped, which we would expect. This is about 240 for a signal to noise ratio and a dB of 23.79. So that makes sense, right? The single channel should be noisier and have less signal than the stacked image. Let's look at a couple other calculators too. So Deep Sky Detail has a couple videos talking about signal to noise ratio, and his videos are very detailed, very technical. If you really want to know what's going on with SNR, go watch his channel. He puts out some amazing, very nice, technically oriented videos. So here's his calculator for signal to noise ratio, and it requires a little work. So you need your DSO plus your sky glow signal, your sky glow background, dark signal, bias signal, your camera gain, the camera's read noise, and then your desired SNR. Now we can get those numbers. Here's my master dark for my 180-second exposure. So it has, my dark signal of 795. And then I have the bias frame here. And the bias frame just has a bias signal of 758. So we can go ahead and put those in there. Then we can go ahead and draw some preview areas. So this is right around the core of the galaxy we're looking at. And then this is just the sky off to the side of the galaxy. So for preview 1, we have a median here of just about 4,200. So we can go ahead and put that in there, which is our DSO plus the sky glow. We got the sky glow in preview 2, which is 4024. So we can go ahead and put that in there. Then I can go ahead and get the gain. I'm using Unity gain, so that's just 1. That's easy. I can get the read noise down here of about 1.6. Then I can get the ideal dark current here. That's about a negative 15 degrees, so I was 0.008. So now we have quite a lot of numbers that we can go ahead and put in here. And we get that my initial frame here had of 1 sub, a signal to noise ratio of just 3. That makes more sense in my mind than the Pix Insight script saying it had a signal to noise ratio of like 200 some, right? And this says that I should get about 5 hours of integration to get a nice signal to noise ratio. And 5 hours is what I aim for RGB on shooting galaxies and stuff. So this is really in line with my thought process, at least what I like behind my exposure times. So Deep Sky Detail seemed good. lot of different numbers you got to put in here. Kind of a pain to pull all those numbers out and stuff, right? Also, there's actually no, if you notice, there's no measure of noise in here at all. And what it does is it's estimating the noise based on all these different parameters in a theoretical sort of way. So there's no real true noise that we're inputting anywhere from your image. And it's just based on the theoretical model of these few parameters. That absolutely does not capture all the noise in your image. And then the next calculator we could look at is the one that Dylan O'Donnell just put out. And here is my single frame. And in this case, we have a SNR of 754. So this one is saying it's maybe 3 times higher than the one in PixInsight and substantially higher than the one in Deep Sky Detail. And if we look at the stacked frame then, here's the stacked frame. Now this one's saying it has an SNR of only 45. That's probably more in line with the stacked one, but for the single frame result itself, very poor calculation here, in my opinion. So it definitely didn't capture the true signal in this frame. It's probably thinking the sky glow is signal. This is a calibrated frame, so that is either light pollution or sky glow in there, and that's what's probably throwing off the SNR calculation. On the stacked one, there's actually more signal in there, so it probably had a better time discerning that there should be some signal in there, giving a more realistic result of 45, which is hugely less, again, than the PixInsight script SNR of the stacked one, which, if we remember, it was a dB of like 30 something, and the SNR was in the thousands, right? The other game we can play is we could just put a very small pedestal during our stacking. So in this case, this is a 0.01. So it's just the image shifted up by 0.01. We didn't add any signal. We didn't add any noise, nothing like that. We just have the initial one and then one with a very small pedestal on the bottom. Now, if we run the image analysis on the one with the pedestal, we get 40, which is higher than the 39. So even that little bit of pedestal, which is not signal, now that's showing that this is even higher decibels, which we know isn't accurate. When we put the stacked image in with the very slight pedestal, so this is the original, an SNR of 45, and when we put in the one with the slight pedestal, now it has an SNR of 51. And you could just see when I click between them, that little line moves up. So again, we didn't add any signal, we just put a pedestal on the bottom of the whole thing. So none of these SNR calculators are calculating SNR. And the reason is, what are they measuring? SNR is not a holistic view of an image. Signal to noise ratio varies across the entire image. Every little region has its own signal to noise ratio. Looking holistic at an image doesn't tell you what's going on with your image at all. The only thing you can probably do is compare a single frame to a stacked frame and see, oh, yep, the SNR went up on these holistic views. That's not how you're supposed to do this. There isn't a single SNR number for your whole image. If you are doing astronomy and you're trying to measure the signal strength of some gas in a nebula, you're going to have to define that region where that gas is, and then you have to subtract the background off of it to get the signal in there. It's almost like you need to do a mini continuum subtraction. But in this case, you need to subtract the sky glow and stuff in a much more similar way to how Deep Sky Detail has you put the sky glow background in there. so it can subtract that off. But in this case, there's actually no measure of real world noise, just a theoretical noise. So again, that's kind of where the shortfall is in this particular one. It's doing a great step by removing that background. But again, there's no calculation of the real world noise in your image. So now we can get to the script I made. It's an easy script. You may have already seen it in the dropdown. It's been there for a while. It's called Object SNR Calculation. What you need is 2 previews, and that's what I have in this particular case. Preview 1, or any preview, is the area you're defining as what you want to measure the signal of in that region. Preview 2, you have to define some other background. Some background that you are subtracting off of the main image. And then just click Calculate SNR, and it goes ahead and calculates it for you. In this case, we have an SNR of 15. It's just 12 decibels. That may come as a shock that the other tools calculate so much higher. And that's because they're given a holistic, broad number for the entire image that includes the pedestal, the sky glow, all this stuff that is not signal, that isn't signal. But that's what's included in those other calculations. Now let's go back to our single frame here, where there is almost no signal at all, maybe just a little bit here in the core. And we can go ahead and run the same Object SNR script. Preview 1 was where we're trying to calculate the signal. Preview 2 is the background. And now in this case, it's showing that we have a signal of 0.6 or a negative decibel. That just means the noise is more dominant than the signal itself. And that's apparent. Like if you zoom in on this preview, there is more noise than there is signal. You could just see it visually. And that's the truth of how you have to do these kind of SNR calculations. You have to have a defined region where you want to calculate the SNR of, and then you have to have another defined area such that you can subtract off the sky glow and everything. Once that's subtracted off, you can go ahead and measure the noise in there. You can measure the signal strength, divide the two, boom, you're done, and you can actually get your measurement. But what does that tell you? If you're doing astrometry or actual science, it can tell you a world, right? You're trying to get ratios of hydrogen alpha to hydrogen beta, or hydrogen to oxygen ratios, things like that tell you the temperatures and nebula, velocities, things like that. If you're doing science, great. You probably need the SNRs. For our case, and I'm with Dylan when he said this in his video, it doesn't matter. You know what the solution is. Integrate more. That's how you get your more signal the longer you can integrate. Ideally, you integrate as long as you can for an object. And you always have to remember that if you want to double the improvement, you need 4 times the amount of integration. It goes up as the square root. That's the big takeaway of SNR. Since it goes up as the square root, and that's the best case, any doubling of improvement of SNR that you want, you have to do 4 times the integration. Just doubling your integration will only give you a 40% improvement. I do want to demonstrate one more reason why just looking at SNR really doesn't matter. So I have the region near Cedar here, and we have a spot with nebulosity, and then we have a dark spot we're going to use as our background to subtract from. So let's pull up the object signal to noise ratio calculator. We'll calculate the SNR. It has 5.6 or a dB of 7.5. So pretty low, but it is what it is. But if you go ahead and do something like, we'll just run convolution and just make everything blurry. There, now we're nice and blurry. If we go ahead and just run the SNR calculation again, oh, now it jumped all the way up to a 73. Because the noise is gone, it got blurred out. But is this image better than the other one? You know, no. The other one's much sharper. It may be noisier, but it's much sharper. And this is the same reason why like big pixel size in cameras are better. It kind of blurs out some of that noise. It's a bigger light bucket. So SNR is not everything, right? Technically, this image has much higher SNR than this image. But which one do you want to be working with? I hope this cleared up some things about SNR that have been bothering me about these calculators, and especially the one in PixInsight, which just gives you wildly fanciful, unrealistic high values of SNR, right? Here's our case. Our true SNR is low. It's less than the noise. But, you know, it's saying that SNR is fine. You're up in 20. So my takeaway is don't worry about SNR. Integrate longer if you want a cleaner signal. And that's just the truth of it. Darker skies and longer integration. Thanks for sticking with me on this little rant. Please comment, like, and subscribe.